session is on metadata. We're already realizing the challenges with the metadata and different kinds of metadata. We have 3 speakers in the next session, 20 minutes each, roughly 12 to 15 minutes of talk, and then remaining time for quick questions. And please continue to log your questions on the challenges that Kati sent the link to. So our first speaker in this session is Paul Macklin, who is from Indiana University. He is an associate professor and the director of the undergraduate studies in the Department of Intelligent Systems. He's a seasoned mathematician and has been using a number of computational tools for us to understand the diverse problems of biology, including cancer and tissue engineering and immunology. And we are very happy for you to talk to us in the next session. The title of Paul's talk is Kidney Metadata and Ontology Design. Welcome, Paul, and please take it over. Thanks.
So thank you very much for that wonderful introduction. I'm very honored to be here with you all today in the presence of some really cutting edge work. These are really the dream data that we as mathematicians have always wanted to work with for a long time. So it's incredible that the NIH and others have really had the vision to assemble this for, which is going to be a resource for years to come. I'm here not really as myself, but as a representative of a broader effort here. The entire IUMC team has been working on this ontology development, and particularly the underlying names here: Sam Friedman, myself, Ellen Portoris, James Sluka, in particular, really led the work to develop this ontology-based method of organizing the data coming out of the TMCs. And as you'll see, even not just us alone, but this has been part of a broader consortium of people reaching out to the TMCs and getting their domain expertise to really make this a team effort that spans across the HuBMAP. There's not really any one person or group. How do I do this? This thing? Nope. Oh, there we go. That's working. Okay. When in doubt, just use the mouse. Okay, so just to give some motivation of how this works, and we'll try to keep this brief so there's more time for discussion. As you've seen, in the wonderful introductory talks, and we are trying to really aspire to map the entire human body. And so how do you robustly navigate through the human body, accounting for variability from person to person? And one way to do this is start thinking of this in terms of contained, in terms of an ontology. You can start at the whole body level, and then you can go say, well, within the body, there are multiple systems, say the digestive system. And within the digestive system are contained multiple organs, like the liver. And within the liver are contained multiple smaller structures, like lobes or lobules. And within there, you might actually have some kind of a local coordinate system in Cartesian coordinates, where you might map all sorts of segmented structures like cells and other things that are extracted from microscopy, as you've seen in just the amazing talks in the prior talk. And so our original idea was to really come up with ontologies that help you facilitate this hierarchical navigation of the human body, to start from the top and go the way down. The thing we've learned in the past years is it's not as simple as we had hoped, and that it's not a simple hierarchical top to the bottom, but there are also all sorts of side branches, and it's really more of a graph than a hierarchy. But a hierarchy is a place to start, and it has motivated our initial thinking. And you'll see more talks, I think, going through the day on how do you improve this notion of a hierarchy and interlace it with really a proper graph, and think about the functional aspects that you map onto that hierarchy that help facilitate your mental model of how you navigate the human body. And so this has really been the motivation, to learn how to navigate individual samples placed within this broader context. And then as you start placing more and more samples, how can you facilitate other methods to start cross-linking samples and to really learn across them, to look for the commonality and see, is there a consensus model of the kidney? Is there a consensus model of the liver that you can draw upon many samples and learn from them? Well, you can't do big data if you can't even write the data down. So you better start with some kind of a common coordinate framework for the individual samples. And as those ontologies work out, it helps you both to organize the data, and it provides an interface to help you search across the data and to filter across features. And Jim Sluka, in particular, has really been instrumental in helping us with that aspect. And then in the sprints of this team, working with Bruce Serra, the CCF ontology development has really been driven by helping to facilitate the way the data are presented. And so there's this integration. The CCF has not been developed in a vacuum, but has really been working in crosstalk with people wanting to do data visualization and other use cases. And then, of course, working with the TMCs to say, here are the data as they are. What kind of data do we expect? Which I think brings us to the next slide. We really need to be able to plan for really highly heterogeneous data. We just saw amazing talks on just a beautiful wealth of data available in the liver, in the kidneys, heart, and other places. And you expect a broad variety of data types and a broad variety of data resolutions. And so it's quite a challenge to say, how can we represent these data? And just begin by capturing these data and providing them in a unified format, and then beginning to integrate them. And you already saw wonderful work to fuse those data. And so just kind of looking at some of the data, and you'll see this, I think, already more. You already saw a great talk on this. You'll see more throughout the day. We expect tons of data and a variety of data, including patient-rated data, data about the individuals, data about the sites, and of course the molecular data at various scales. And so the goal really, again, is to both help us to organize the data and to facilitate its navigation and to be able to filter on it, to find it when you're looking for it. Because one thing we found, my colleagues' wonderful, and Liesel's wonderful user surveys at the beginning of the year, if you asked 15 people how they'd like to access molecular data, you'll get 17 different answers. And so being able to account for these use cases is important as a driver for the ontologies as well. So to give you a notion of our overall approach, we have some guiding principles on developing this ontology. And certainly one of the most important concepts is to realize that there is already a tremendous amount of great work out there. We don't want to completely ignore that and invent it from the ground up, and instead to mine and reuse good things wherever you find them. So certainly you look at other prior mapping efforts that have been more restricted to individual organs, they've already faced many of these questions. And so HuBMAP in particular and the RBK have done wonderful jobs of organizing data. You're going to hear from Bono later on how they've been working to organize data from their mapping efforts. And so wherever we can, we've been trying to already look at data formats and ontologies that have been developed by other efforts to say, can we find the commonalities between these different formats? You often see kind of convergent evolution, that different groups facing similar questions and similar pressures will often converge towards very similar solutions. And so can we find those commonalities and take the best from different efforts and leave the worst behind has been kind of our goal here. Then if you go into domain-specific areas like imaging, we can certainly learn a lot from the open microscopy environment work and TIFF as great formats for storing data. There are wonderful emergent formats for storing microwave experiment data. And then I think you've already seen, we want to leverage the domain expertise within the HuBMAP. And you realize that each of the TMCs is a leading expert on their individual organs. And so the best place to get good information and insight on how to map the kidney is to talk to the kidney TMC. And so you already see, as we'll present later on and throughout the day, that we've been reaching out and leveraging that expertise. And that's something we're going to see going forward in year 2 and beyond. And then to facilitate that all, realize that ontologies in general have developed wonderful tools to help you facilitate working with those ontologies. So we have standardized on using OWL as our ontology data format. That once you standardize on that, you get access to a whole host of tools that facilitate the work. And then as necessary, we developed our own work to help cross-link these and to form these graphs to help you really navigate through the ontologies. And so to give you, we're not going to go through this list, but this reference material will be here. But as you go through different aspects of the data that you want to look at, there are already existing ontologies that we can make fantastic use of. Some of the more important ones are Uberon, FMA. The cell ontology has been very helpful for cell types. There are various ontologies for metadata that we've been making use of. And of course, Mesh and NCI Thesaurus will give you great dictionaries of terms, although those would have less of an ontological structure and would be more, well, a dictionary. So that's been our guiding principles for developing the ontologies. To give you, just a status now, you can click on this hyperlink in our slide deck. You can actually access a live version of the ontology. This is really thanks to a great interface between Jim Sluka and Sam Friedman and Bruce Hare, second, on interfacing this together. And so you can see on the right, a very zoomed out of our early ontology. It's been started out saying, can you kind of start at the human body level and then just get into the various systems and look at the data that we already have, which is primarily kidney and heart. You see it's a fairly simple ontology, but already quite a mess. You can zoom in here more, and you see that we have an anatomical system. So this is very inherited from the Uberon. And then you get in and say, finally, we're at kidney, and then you go in and you get all sorts of different data types. And it gets to be a mess in a hurry, and you expect this mess to get much bigger as we start adding on more systems for the other TMCs. But you can see that there's already quite a bit in place based upon this first year of work. Rather than navigating through the whole ontology, again, I encourage you to go back and take a look at this. And really, the approach has been to start with tables of requested terms and work with the TMCs, and then go into the Uberon and add these in, and then develop the graph that connects it all together. And so this is something we can do on an organ by organ basis. Now, within the ontology, we've also found that our work has had to expand in scope, because it's great to talk about ontologies, but we have to actually be able to store data and talk about data formats. And so that's a bit beyond what we had originally anticipated doing the first year, but as necessity has led us to, we've begun working on it. First of all, OME and TIFF format has turned out to be quite flexible for storing a lot of the raw data and anything that you might be fusing together. It's already got an inherently great way of storing multiplexed data, because what is a color in a TIFF image is more or less a channel in this kind of imaging. And so you can easily extend that to 3D or 4D if you want to go in time. So that's a really fantastic way to, in a standardized way, store the data coming off of the different instruments that are spatial and often volumetric. And of course, there are wonderful data standards out there for volumetric data that we can use too. But that's just the raw data. We need to capture not just the data, but the knowledge. And so you look at a lot of the workflows, and you heard already today, a lot of the work is segmentation. You find the cells, and those help you divide these tissues into interesting things. And then within the cells, you say, now what was back in my original channels? What were in these different cells, and which proteins popped up where, and start annotating these. So you end up with vectors of annotations that you want to overlay on top of the original data. And so there are ways to do that. First of all, if you find regions, you can use things like SVG to help annotate those. And so those are like data overlays. In particular, then you have vectors of data, say, find all the objects in this screen and associate some vector data that you have represented and save them in some sort of a format. And this gives you a way to kind of add vectorized annotations to the spatial rasterized data. We in our past have worked on this in a computational framework called multi-cell DS, where we have had experience with this. And the beautiful thing about computation modeling is that you already have your segmentation done before you begin, because you have a bunch of cell agents. But it gives you a wonderful way to practice saying, if you have segmented information, how can you represent that data and capture it? And once you use that knowledge and bring it back to the experimental field, it gives you a natural way to start bridging between computational biology and experimental biology and imaging. And so going forward, this would provide a great way to take information extracted and knowledge extracted from the different TMCs and start putting into computational models that help you extrapolate from static images to dynamics, and to understand the function of the tissues, and saying, if these are our hypotheses of how cells work and act together, do we get the picture that we see in the TMC? Of course, we need to talk a lot about metadata. This is, again, not originally in our focus for year one, but indeed has become a focus for year one. And so you realize that there are a broad variety of types of metadata that do need to be captured. Both the biological and clinical data about the individual patients. That you want to understand if there are racial or other differences between individuals that become manifest in the molecular data down below, and help you understand the diversity of patients in your sample sources. There are technological metadata. How are these things measured? On what instruments? With what resolution? What do we know about the variability and errors of those particular instruments? Because that's very important metadata for understanding the context of the data. How are they measured? There are interpretive information, such as what workflows and algorithms do you use to extract data and knowledge from your raw data? How did you do your cell segmentation? Could it be improved? How did you do your data fusion? There's also provenance information. Who actually did this work? Who's the point of contact if I have a question? And heaven forbid you find out that someone did data falsification and you have to do a retraction. Can you find a specific data to retract instead of having to throw away the entire data set? That could be very important for quality control down the road. So you do need a chain of evidence. You don't want to be in this case where you say it's all or nothing and you have some bad data and you have to throw the whole thing out. You don't want to change the entire data set. And of course, there's use metadata, and we've had committees working on this and saying, what are the licenses for the data? This should be embedded in some way in the data set so that if you download some part of the data and mix it with something else, you remember the use rights and remember the citation information. And that certainly helps to encourage sharing of data if people can get proper citation for that data. And so we have been working over the past year on how to collect this information. HuBMAP has given us a lot of insight on how they do it, and you see that there are wonderful instances out there. So this is not new and never before considered, but we have a lot to learn from to drive that forward. A challenge is that even if you have the same metadata written down among different groups, there might be different ways of recording the same information. You might have different data fields. Some might be working in meters, some might be working in centimeters. There are all sorts of ways that need to be reconciled. And it's often just a matter of sitting down and matching these up one by one and providing data transformations. But it's important to remember that even when you're writing down the same things, you may not have the same way of writing it down. You have to be very careful about that. And there are standards out there that have been developed now over the past year to try to start collecting that information and harmonizing it across the different teams in the Hive. Writing down this information, and that's been a nice focus of this mapping center. In year 2, there is more explicitly part of the deliverables. And so we are now starting to write down some set of metadata to be collected across the different TMCs, which will help to harmonize already. So that's kind of an overview of our work, and just kind of give you a sampling of the next steps, and just start with some discussion points. In the next year, we really hope to start finalizing these metadata formats really in conjunction with the other TMCs and to start rolling out a unification of the data formats that are going to work well with the different technologies across the TMCs. That takes a lot of work to make sure that it's standard and unified, but not too restrictive that people can't roll out new technologies and feel themselves too constrained, but they can't apply the best of what's out there to their particular work. But that's been a nice work in progress. And then to start working more closely with the different teams and with the TMCs to really roll their knowledge into the common coordinate framework. Other questions we have, are there unmet needs, and are there any less should be in the ontologies to describe your particular data? We have ways to take that feedback, but it needs to be a dialogue. So I think happy at this point to open it up to questions, and we'd be happy to direct those questions to Jim and to other people as we need to.
Thank you.
Thank you very much. Yeah, we have 2 minutes for quick questions.
Yeah, we do have a question.
Next one.
I don't know if you want to read it.
Let's see. So please note that just because an ontology is present in Oberon, it may not be appropriate for HuBMAP and will need to be vetted by experts. Ontologists are not content experts. Also, we need to have a conversation about controlled vocabulary.
Absolutely. And so Oberon has been a wonderful launching point, but we found a lot of our work in the past year was to actually go through those terms and figure out which ones were actually appropriate, which ones ought to be called. And that has really required a direct dialogue with the different TMCs to get that domain expertise. Oberon's a start, but it's definitely not the answer. And we definitely appreciate and agree with that point. I think ultimately we're going to be able to work with, you kind of have this broad context framework to say, here's the whole body ontology and the unified ontology, but then you're going to get down to sub-ontologies, organ by organ, and that's really where it takes a dialogue with each individual TMC to work it out. The good news is that there are only finitely many organs, so that's that's a bounded amount of work. Yay! But practically speaking, it definitely is going to require a lot of dialogue, and completely agree with that point.
This is Samuel Friedman chiming in. I've also had discussions with LungMap, and to extend what Paul has said, that there are other ontologies that will extend really beyond Oberon or to get to the organ level specific information that we need, and to be able to then have those ontologies cross-link with the other ontologies that we're already looking at besides Oberon.
No, those are really great points. And the problem with Oberon is that it applies to everything, including embryos and flies and things like that, and to really make sure we can cross out the things we want. And that was really a goal, is actually to start with the minimal terms we needed and then connect the pieces as much as we can without pulling into things that we don't need or actually inappropriate. But there's no substitute for domain expertise in that curation.
But you have to remember that generating a deep ontology of kidney is a couple of man years of work. And we're talking about a project where we're going to do this 10 times. So there is going to be some point where we're going to reach, and we're just going to have to go to that community and say, give us your best ontology. We're not going to judge it. We're not going to vet it. We don't have the time. We don't have the expertise. That is that community's ontology. Not only do we have tissue ontologies, we're going to have an ontology that is just as complex for every technology. Microarray ontology is just as complicated. So, you know, it's easy to say create an ontology, but it's a tremendous amount of work. And we're going to really have to depend on the individual organ communities, individual biotechnology communities, individual imaging communities to do a lot of that heavy lifting for us.
I think that this comment is very appropriate and very much related to what we'll see presented in the ontology section coming up. And so I think it's good to have the set of information and then have those discussions. But I think the notion of writing ontologies and frameworks in this context of this project is highly problematic. I agree. And leveraging technology ontologies must be the way to go for two reasons. One is synonymy, and the other is integration with other things. And even setting aside the tremendous work and problem with being ontology creators in the context of this project, those other two reasons override even the work.
So it looks like you're giving my presentation already.
So in terms of trying to,
You know that there's a big point of discussion here.
I think let's move on.
The scale of that discussion, and then we'll put it off a little later.
How about, I know we have ontology session coming too, so it's great, I think, to have these points raised. These are all valid points, and thank you, Paul, for this nice presentation, for laying out the complexities of metadata and how to harmonize them.